Okay, so today we will start talking about a more abstract layer of processing natural languages. We talked so far. We only talked about the words, right? We looked at the edit distance. We looked at the morphology of the words, and we didn't move up from the word level. Now we are going to move up from the word level to talk about the complete sentences and complete paragraphs and documents. And the technique that we are going to use will not use actually any grammar information or morphology information or any semantic information, but it will capture most of those information, most of the information about those layers in a very simple way, actually. And we call this language modeling using the statistics. Very simple approach, but very, very effective. Very, very good results out of this simple method, and we are going to look at it. Next week, by the way, is our midterm exam. Yeah, that's what we said at the beginning of the semester, right? This November 8th is the. Didn't we say that? So let me see. Where is my syllabus? Yeah, here it is. That's why, because next week is the 7th week of the semester. That's the mid-semester. Where are my?
It's been already 7 weeks.
Well, you have been sleeping in the class, yeah. It is, yeah. 7th week, November 8th, Monday, tentatively. So next week is the exam during the class time. Okay?
So exams will be face-to-face.
Exam will be what?
In class. Face-to-face.
Yeah, sure, yeah. Well, of course it is face-to-face. Exam will be face-to-face. You will have mask, and I think I will use this room, maybe, but this room may not be enough. I think I will try to arrange something downstairs. If so, I will get you downstairs, and it will be a 2-hour exam, and I won't do any classes, any lectures. Okay? So up to this point, everything that I covered in the class will be. You have a question? You are just expressing your surprise? Yes. Okay. So, I mean, you will get the same surprise when I say next week is the final, and 7 weeks will go by like that. Yeah. Okay. So next week, November 8th. Okay, at midterm exam. Closed book exam, face-to-face in the class, and it will be 2 hours, and all the materials that we covered up to the end of this lecture today. So we are going to look at this word prediction task, actually the language modeling again. We are going to develop a model to the language, any language, Turkish or English or French, doesn't matter. This language will predict which word should come next if I give you an incomplete sentence. And we are going to do it with the statistics, meaningful statistics and computable statistics and easily compute statistics. Okay? And all the knowledge that we are going to use are actually you already know. I am not going to give you any new algorithms, but it will be kind of a new employment of what you have already know about the statistics. Okay, good. So just to overview of what we had now. Okay, this is definition of the conditional probability, but I mean, not that I am just stressing the definition part. This is by definition, the conditional probability is defined this way. So it says that this is how you read it. Given B, what is the probability of A? Okay, I know that B has happened. What is the probability of A? A and B are events, okay? If I am a doctor, if I see a patient, and I see that patient has fever, B has happened. Given that patient has fever, what is the probability that the patient has the flu? Okay, that's one thing. Or given that I know my previous word is the, what is the probability of the next word being man? Okay. Okay, it is very high. Maybe it is maybe 0.01. It's high, right? Given that the previous word is the, what is the probability of having the next word, for example, gun? The gun, I mean, like this. I mean, I am sure there are uses like this, the gun, but it is not very probable, right? It's not very probable. So if I can measure these kind of probabilities, then I am kind of fitting a model, a statistical model to the language, Turkish or English. Then I could use it in many places, like which sentence is better if I am doing a translation, this one or that one, okay? Which word should I replace this word with if I am doing the spelling correction, okay? Let's say I am doing the spelling correction. I saw that there is a misspelled word, and there are two words that have the same exact edit distance with the original misspelled word. Which one should I use? So I'm going to ask this to probabilistic model. Okay. So previously our models were. Can we open the window like that? If you are not, I mean, yeah. Okay, so that's what we are going to do. And what does it say? So remember, this one is fever. I have fever, and I like to know if I have flu or not. So what does it say? It says that you should do this calculation: P flu and fever over fever. This should be P. Okay, what does that mean? What is the probability of anybody having a fever? Okay, calculate this one. Find this one from somewhere, and find this one. The people who have both flu and fever, and this ratio will give you this conditional probability. So, what kind of other probabilities you know other than the conditional probability? This is sometimes called posterior probability. Posterior because I know something, okay, post-event kind of a thing. And there is, other than the posterior probability, there is what? Prior probability. Do you heard it, right? Prior probability is just this. What is the prior probability of fever? I mean, what is the probability that any person that I see in the street has fever? Okay, that's the, without knowing anything about that person, what should I do? That's the prior probability. Again, this one is the prior probability of anybody having flu and fever together. Okay, but this is posterior probability, very, very important. Okay, so usually doctors or any analyst that does the diagnostics, they would do that kind of stuff. What is the probability of flu if that person has fever and is coughing and he feels sleepy? What else? What kind of other symptoms do you know with the flu? He feels tired, and what else? Headache. So if I go to a doctor, if I say I have fever, cough, sleepy, I am tired, and I have headache. So all of this stuff, usually they have a mental model. They say, okay, you got flu. And sometimes this is not enough. They ask you to run some lab test, okay? Lab test one is 0.7, for example, they count some kind of a number in your blood analysis and etc. Okay, so this is what they do. So they use this posterior probability, and the more this is the evidence part. This is the evidence part, and this is the result that you like to get. Now, is it a healthy person or a person with a flu? Okay, so that's what we are going to do. But of course, we are not going to do the medical diagnosis here. We are going to do the same thing with the words. I have seen all of these words. What is the probability that next word is this one? Okay, so there is an example that I have stolen from Wikipedia. Okay, there is an event A, and there is this B1, B2, and B3. Okay, so it looks like this is the whole space. So the sigma is the whole space that can happen, everything. So the total of these numbers should be 1.0. I guess it is, right? This is 0.4, and this one is 0.5, and this is 84, and if I add this up, it will be 1.0. So what is the probability of A? Probability of A is 0.3 plus 0.1 plus 0.12, right? So that's the probability of A. It is 0.52. How about this one? Given that B1 has happened, what is the probability of seeing A? Given B1, what is the probability of A? How do you read this in Turkish? Given B1, probability of A. B1 olmuş varsayalım, A'nın olma ihtimali. B1 verilmiş, A'nın ihtimali. It is not B varken A'nın ihtimali. It is, I assume that B1 has happened. I know that. Either from evidence, from observation, or from assumption. I know that B1 has happened. What is the probability of A? Okay, so prior probability of A is like 50%. Prior probability of A is 50%. So what do you think that P given B1 probability of A? Do you think that this would have a higher probability or
higher probability? It should be 1, I think.
Given that B1 has happened, the probability of A. Why? Because I am already saying that B1 is, so let's put it in the formula. What is the formula? Formula is PAB A comma B1 over P B1, right? What is the probability of B1 PB1? It is 0.1, and this one is 0.1, right? Because both of them are happening, so it is 1. So what does that mean? If I know that B1 has happened, what is the probability of A? You're already telling, okay? So it is something like this. It's something like this. It's something like this. If I am, what is this F? I don't know what this F is. This should be I know what it is. Yeah, it is the function mean. Yeah, because in the morning I was giving the C++ lectures. Sorry, I wrote lots of functions today. Sorry. If I am, let's say, if I am in this classroom, okay, my location is P location is in classroom. If I am in this classroom, what is the probability that my location is in GTU campus? Something like that, right? So it is 1.0, of course, it's something like that. So so it worked as expected. This is 1. How about given B2 probability of A, okay, given B2 probability of A, this won't be, okay, let's calculate this. Given B2 probability of A is P A B2 at the same time, and P B2 is going to be, what is the upper side? It is 0.3 12 and B2 is 0.16. So that's it. What is it? It is 3 over 4, right? So 0.75, 75%. Okay. And this one is interesting too. Okay. What is the, if I know that B3 happens, what is the probability of A? It is 0. It's like, I am at home. What is the probability of, I know that I am at home. What is the probability that I am in GTU campus? It is 0. Something like that. So we are going to use this definition. Again, there is no proof that such an equation exists. This is the definition of the conditional probability. Definition of the conditional probability. Using this definition, you may write other stuff, right? You may say that. You may say that. Well, in that case, like, okay, P A B is equal to P A B times P B, right? Just do the opposite thing, just the other way around. Let's change A and B. So this is B and this is A. The upside will stay the same. This is going to be A. If I write the same thing again, PAB will be equal to PBA times PA, right? So this one is equal to that one. Okay, so that's a nice equation. Okay, this one is a nice equation, and I will use it in many places. And in fact, using this equation, I can write this, right? P given B, the probability of A is A given B given A times PA over PB. Okay, that's called the Bias Theorem. So Bias Theorem comes directly from the definition of the conditional probability. Okay, so we use this sometimes in lots of places. For example, doctors use this. For example, what did I say before? Let's say this patient has flu, okay, flu and no, fever, flu, then this is fever, and this is PA is flu, okay, and this one says that if I have flu, fever, okay, calculating this is easier than calculating this directly from the formula here. Why is this easier? Because the important, okay, I can always calculate this one and this one using regular statistics, but this one is something that says that if I know this disease flu, I should know how many times it causes fever, right? So this is the cause, this is the result. Cause and result, okay? But I'm trying to calculate just the opposite. I mean, this is the result, okay? This is the result, and these are the symptoms. Symptoms, result, okay? This one is the cause, this one is the result. So estimating this one is easy for most of the tasks, okay? For most of the tasks. So that's why when you see something like that, okay, somebody's giving you the observations and trying to see, are these observations caused by this root symptom, root cause? Okay, this one, flu. If you are asking that question, then I can give you this equation. That's called the Bias theorem, and it's very important theorem in all kinds of engineering, and in this case, medicine. Okay, all the doctors do. Okay, especially if you are doing some diagnosis, all they do is just they are running this equation in their head. Most of them they don't know that they are running it. but most of the time, this is what they are. That is what they are doing. They have this. Okay, in this season, how many people have fever? In this season, how many people have flu? Okay, both of them. And this comes from the books, right? In the books, it says that flu causes 35% fever with the patients. It comes from the books, okay? This comes from the statistics. Now I can calculate this one. Or maybe let's talk about car repair, okay? My car, for example, consumes too much fuel. Okay, that's my symptom. Consumes too much fuel. That's my symptom. And I like to know if the problem is with my fuel filter. Okay. Should I change my fuel filter? I'm asking the question. Again, let's look at this one. This one says that fuel filter and too much fuel. So whoever built this car, they already have this model. Okay, they know the percentage of the cases where the fuel filter caused the too much fuel. Okay, so this is cause and result. Okay, this calculating this one is easier. This one is not that easy. Going from the symptoms to the cause is not easy. So keep this in mind. This is just a simple reminder of how we do this conditional probability and bias theorem, and we are going to work this out in a few minutes with the words. Okay. Any questions? Any questions from the online audience? Can you guys hear me? It says that I have a bad connection or something like that.
We can hear you, sir. There is no
We
problem.
can hear you.
Okay, good. So let me go back and let's go back to the words, natural language processing. Okay. We are going to do this. If you see a sentence, I noticed 3 guys standing on the. Okay, tell me a word here. Just a word. What?
Table.
Table?
Yes.
Really?
Standing on the bank, maybe.
What? I can't tell it again.
Bank.
Standing on the bank?
Yes.
What kind of NLP models do you have, guys, in your head?
Standing on the stage.
Stage. What else?
On the bridge.
Bridge. Okay, which is the most probable one? Bridge, stage, bank, or table? Well, for the last 10 years, I never seen 3 people standing on a table, actually. Or maybe 1 people doing some kind of a work, changing the light bulb. Well, it is possible, but, and again, Efkan, what kind of places you are going? But, I mean, people usually sit on the banks, not stand on it. Stage I have seen, and bridge I have seen.
I mean bank, money bank.
They are standing on the institutional bank.
Standing
Yes.
on the
Akbank, Street.
Yes.
I
Figuratively standing on the
I don't
bank.
recall anybody standing on a bank. Building of a bank.
Figuratively standing on the bank. So they are like keeping the money for themselves.
He guys standing on the well, sorry, he's talking. I don't remember any idioms that does that. I don't know, Efkan, your NLP model in your head is kind of different. So I'm going to assign a low probability for this one. So maybe the highest probability will be this one. This one is that probably depends on my battery. Okay. Reboot the pen. Okay, so I think this is a higher one. I don't know, 2, 3, 4 is very unlikely. But the thing is this. Nobody would tell me, I noticed three guys standing on the third past tense of this verb go, right? Nobody does see that. Even if Khan could have come up with this kind of a, but this is syntactically completely wrong. All the things that you guys gave me, by the way, just two people. Okay, the others I don't know what they're doing. All the guys you gave me are nice nouns, and grammatically they are correct. Semantically doesn't make much sense. Some of them maybe. Okay, this one, well, nobody can say that standing on the gun is a bad sentence because it might happen. Gun can be used as a noun for some cases, very rare cases, but it can happen. I can say that it is probability 0, but it's very, very low. So what I'm trying to say is this. If I have a model that assigns probabilities to these words one by one, okay, doesn't matter, the functions are correct, the meanings are different, semantically, syntactically, or morphologically, okay, doesn't matter. If it produces a probability for me, that would be very, very useful. That would be very, very useful, okay? So I need to know lots of sources of knowledge. For example, again, morphology. How about banks, tables, stages, bridges, okay? How about going? Okay, if I put there, instead of gone, how about going? Is it better? Okay, so syntax is there too, or morphology is there too. So that would be a very powerful tool, and it turns out that we can calculate this probability by simply looking at the preceding words, all these words, and fairly simple counts. Okay, the simplest thing that I'm doing is this. When I am in doubt, when I'm writing in English or in Turkish, okay, depending on the, let's see what kind of NLP model has, okay, three guys standing on the bank. Let's see if Google has seen such a thing in its life. How many
You
people
wrote,
are there in this world?
you wrote the guys wrong, sir.
Everything gays, sir.
Yes.
Did I say guys? Really? Okay. Let's see what this one. Okay. 6 results.
Okay, that's
Okay.
more than what I have expected.
What?
That's more than what I have expected.
So, well, we have at least Afghan. So, Afghan, you have some friends? Okay. So, this is 6 of them. 3 guys standing on the bank. How about 3 guys standing on the bridge? Is that correct? What? Just 2?
Just 2 results, sir.
Yeah. So bank is better than, okay, so there is something wrong with me, not wrong with the Afghan, yeah? 3 guys standing on, what was the most problematic stage? Stage. Just 1 result. So that's a very rare occurrence. So if you see, Google says that I have all the words, okay, I have scanned all the documents written in English, and I scanned the whole World Wide Web, and I know if there is something digital or printed, I know everything. If you are looking for something like that, I don't, I have seen only once. What? Table? Okay, stick, standing on the table. Whoa. Okay, table is the, what does that mean? Well, okay, I have even pictures of it. They are not standing on the table. They are, so this is standing on the table, just 3 standing. So this has the highest one, right? What?
Who
1.
would have guessed?
Okay, 3 guys. Oh, no, I didn't know. No, that's not correct. I didn't put the quotes. With the quotes, I have,
Oh, no results.
No result. This is 0.
Ah,
Okay. So it is saying that instead of saying, how about this one? 3 guys standing on the, let's see, this one. It says 3 guys standing on the, it happened 16,000 times, standing on the bank, standing on the sidewalk, standing on the street, ledge, edge, corner, street. Looks like street is lots of. Okay. So how many times? 7 times. But this is not a very frequently occurring phrase. And if you look at this, I didn't even write a complete sentence. Right? I didn't even write a complete sentence. So you might be wondering how are we going to calculate this probability if Google doesn't have, I mean, you cannot have more English NLP data than Google. Nobody has it. Okay. And the difference with the second one is very big. The gap is very big. And you might be wondering, if I don't have this information, how am I going to calculate it? We are smart. We are going to calculate this using some approximations, some assumptions, and it will come in a few seconds. Okay, so that's what we are going to do. That's what I do. I mean, if I am in doubt, when I say, should I say this or should I say that? Okay, I write both of them at Google, and which one is higher, then I'm going to use that one. Okay, I'm going to use that one. That's what I do in a simple way, but we are going to do it in a more systematic way. So looking at the preceding results and simple counts will be okay. So for this, we have this formalism. We call it n-grams. Okay, n-grams are token sequences of length n. For example, if I do this, I notice 3 guys standing on the. If I take the 2 grams of it, okay, 2 grams. I notice is a 2 gram or bigram. Okay, 2 gram. Notice 3 guys standing on the. Okay. 2 gram, 2 gram, 2 gram, 2 gram, 2 gram, and 2 grams. So there are total of 1, 2, 3, 4, 5, 6, 2 grams in this sentence. How many 1 grams do I have in here? 1 grams. It is just 1, 2, 3, 4, 5, 6, 7.
8.
That is 8.
The word we are trying to guess. Don't we
1,
count?
2, 3, 4, 5, 6, 7. Okay. There are 7 1 grams. I don't know the 8th one. We'll count that, okay? How many 3 grams do I have? This is 1. This is 2. This is 3. This is 4. And I guess this is 5, right? 5, 3 grams. So counting these n-grams is going to be important for us, because this is what we are going to do basically. We won't ask Google or anybody, how many times did I see how many 3 guys standing on the street? We are going to ask Google, how many times did you see I notice? How many times did you see notice 3? How many times did you see 3 guys, etc. Okay, I am going to count them separately, and I'm going to try to merge them, because see, these are connected. Notice 3, guys, standing, and on. These are all connected. Okay, so that's what the n-grams means, and that's what we are going to use to calculate the probability of a sentence. Okay, so more formally, we can use the knowledge of the counts of n-grams to assess the conditional probability of candidate words as an expert in the sequence. Okay, and we will come up with a theoretically equal way of calculating it using the n-grams. It will turn out to be expensive again, so we will do some kind of an approximation, and that approximation works very well actually, and we are going to see it in a few minutes. By the way, instead of doing this, instead of doing this, there is a very nice Google Ngrams tool, Google Ngram Viewer. You can write it and see, okay, see how many times this happened, and you don't need the codes. 3 guys standing on street is longer than 5. Oh, okay. 3 guys standing. Let's look at this 3 guys standing. And how many times this happened? Okay. So it gives you, since Google has all the printed text, from 1800s to 2018, right? So for some reason, 3 guys standing happened a lot in 2013. But the increase here is, it is, I guess, because they're available to the text and etc. Okay. So this is 3 guys standing, this is happening like that. How about this one too? Okay, do I have just English, American English, what? Oh, okay. There are many other. Do we have Turkish? No, we don't have Turkish. So for the whole English 2018, 2019 case is what's happening. Let's look at this one. Internet. So some people started using internet in 1970s for some reason, and in 1992, okay. I think this 91 is the first time that I heard about internet. Okay. Then after that it just exploded. And it looks like it keeps increasing and increasing, right? Where did the Facebook go? Facebook. Yeah, for some reason it went flat. So it happened, it is all. Do you see in 1950s there is a Facebook happening, there's Facebook going. You know what Facebook is actually? Facebook has a meaning. I think it is a,
The book in the front.
well, it's kind of a table book. It's like you know the journals, graduation journals, we have the pictures of everybody, and underneath you have his or her information. So Facebook is that word. So people use the Facebook like another word, but before 1950s it didn't happen, right? So they started using this Facebook in 1950s, but after 2000 just took off, and now it's kind of flat, and we are hoping that it will drop back. Okay, so this is Ngram Viewer, and we are going to, this is not a complete sentence search tool, it's an Ngram Viewer. So how many times this 1 gram has happened? Okay, how many times Facebook is bad happened? Let me see. So what it says, no valid Ngrams to plot. So it doesn't say Facebook is bad. Couldn't find it. Should I? I think this shouldn't have any. Is case sensitive. Oh, let me do it case insensitive. And do I have anything? No, it doesn't say. It says Facebook is bad. Well, I mean, if you don't have enough number of occurrences, it doesn't count them. How about Facebook is? And this, and so it looks like, so what is the difference between, oh, okay, so case sensitive and not case sensitive. So if Facebook is something, it's doing it, but I don't know what is the third one. Maybe we can ask it later, okay? So let's come back. This is a tool that we will remember to use. And for the application, this is what we are going to do. For automatic speech recognition, okay? So remember, the sentence, remember what was the sentence? I made her duck, right? So remember, if we are doing the speech recognition with I made her duck, there were lots of sentences that I interpreted from the speech recognition. They all included the correct spelling words, but the words didn't come together in a meaningful way. So if you put all of them in this model, it will give you the probability of it. So I can use it with the automatic speech recognition system. Also, handwriting and character recognition, spelling correction, machine translation is important. You translate one sentence from Turkish to English. Probably there are many alternatives to translate it. Which one has the higher probability, and many more. So these are the applications. As you see, I am not running any natural linguistic related algorithms. I am not saying this is the morphology, this is the grammar, this is the semantics. All I'm doing is just the counting of the words, just counting. Okay? Good. Any questions so far? Any questions? Okay, let me stop here for 15 minutes. Let's be here around 14:32. Kimse yattırmadı ki daha yüzüne.
Ben hatırladım. Boş herhalde. Birisi var değil mi? Sıra boş. Sen taraf boş mu? Sen taraf boş mu?
Ve geçen yılda tam kamera üniversitesi. Karşıdayız. Onu sevdim. Şöyle gitsek.
Nasıl güzel oldu ya.
Lastik arası. Onu da onu yapacağız.
Bak nasıl güzel.
Neresi? Manzara o. Neyse. Daha şu bulursam. Hızlı geliyor. Ne yapalım?
Daha da yok.
İyi ya. Şeyde mi?
Şeyde mi kalıyorsun? Birlikte mi kalıyorsun?
Evde dışarı çıkan kayra girer.
Olmuş sizin yayınlara.
Okay.
Kardeşim şunu kapat. Çok yıkıyorum.
Okay, so the thing is this: counting, we have to do it in a smart way, because if we are trying to do whatever what I did before on the Google example, even the simplest sentences, you will see that it will not happen. I mean, for some reason, human language is like that. Even the simplest phrases like, I saw 3 guys standing on the street, did not happen at all. Okay, nobody has said such a thing on the World Wide Web. It is not printed anywhere, etc. So this is going to happen, and if those phrases do not happen in any place, how are we going to calculate the probabilities? Is a problem. Let's look at this one. He stepped out into the hall and was delighted to encounter a water brother. Okay, so if we are doing this sentence and trying to measure its probability by asking the Google how many times it has happened, it's going to tell us that it happens 0 times. That's it. Okay, that's not going to be good. So in that case, that's what we are going to do. We are going to do this 1 gram, 2 grams, and 3 grams to calculate the sub-probabilities, and we will put them together to calculate the whole probability of the sentence. So counting is something that we are going to do. So in this case, if we count 1 grams of it, 1, 2, 3, 4, 5, 6, comma is another word. It's important. Okay, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, there are 15 tokens in this sentence, and 15 1 grams, 14 2 grams, 13 3 grams, and etc. It goes that way. Okay. Sometimes if we are doing, I mean, counting is not that easy. Sometimes, for example, if you are doing speech recognition, people don't talk like they are reading something. They always pause. They insert stuff like or etc. And sometimes they repeat what they are saying. When I say, see, I am repeating when I say. When you are doing the speech recognition, things are different. For example, somebody can pronounce a sentence like this. I do mainly business data processing. So as you see, I inserted this a sound without any meaning. And instead of saying mainly, I first said main, then I said mainly, etc. So this counting with the speech recognition is even more difficult, but I think for now we are going to ignore that part and we will continue with the regular written English or Turkish. Okay. So when we talk about the counting words, maybe we should make some differences between the individual words and words that happen often. Okay. In this case, there are 18 tokens, again counting the punctuation, this punctuation. Okay. The is used 3 times, so there are only 16 unique types. So token is every time word is happening is a token, but the token they happen 3 times. Okay, they are types. So this is kind of a terminology. Okay, so we will have to focus on counting both types and tokens of both words and engrams. Another issue is when we count stuff, should we count morphologically different but root-wise same words? Okay. For example, when I'm counting cat, should I count cats as cat or cat? Okay. Should I going and go as the same type, etc. So singular and plural ones. Should I mix them together and etc. These are all has to be considered together. Usually we consider them as different words, but in Turkish situations where, for example, in English, you have only this problem, cat and cats, and that's it for nouns, right? But for Turkish, we have the possessive. Should everybody sign this? Okay. I have 2 or 3 people. Mohammed, you don't sign up? Where is Mohammed? So you didn't sign up? You didn't register your name? No. Okay, because this doesn't count.
Baktım ama yoktu.
What?
Dün akşam baktım da yoktu belki.
So it was available today. Everybody added it. Okay. If your name is not on that list, I am not counting those. Okay. So word forms are again important. So what should I consider as a word form, plural one, singular one? These are the decisions that has to be decided, but I will keep these kind of decisions out of the discussion of word counting for now. Okay. So this counting corpora, there are some very old corpora that keeps these word counts. One of these earliest ones is the 1992, when the internet started becoming a thing. Before that, they did that. Okay, there is this brown corpora. There are close to 300,000 word form types, and total of close to 600 million word forms. Okay, it looks like it is large, but compared to Google, it is not that much. Google says that I have read this many tokens, this many words. I think this is 1,000, million, billion, trillion, and what is after trillion? Quadrillion. Okay, I believe you, whatever it is, but it is large. Okay, 10 to the power 12, 13. Okay, and there are 13 million word form types. You will say, well, in English dictionary, we have only 100,000 or 200,000 names, and the words. Where is this coming from? But it comes from all the numbers. 72 is a token. Okay, 75 is a token. Misspellings, lots of misspellings. Names. Okay, proper names. Names of the towns. How many towns do you think are there in the world? Okay, so each one has to occur in and acronyms and etc. So if you add them together, there are 13 more than 13 million unique word forms happening in the Google corpora. Okay, Google corpora. But you might say that this corpora with that many tokens should include all kind of possible sentences. No, even the simplest one that I showed you, and that was the complete sentence, it was not in the Google. Okay. So back to word language processing. This is what we are going to do. We are going to say that I have observed word 1, word 2, word 3, up to word number n minus 1. What is the probability of this word number n? Okay, that's what we are going to do. We will try to assign a probability to this one. Okay, these are my kind of evidences. This is what I have observed. Okay, what is the probability of next word if that word is street or bank or table, whatever. Okay, and we are going to call this model a statistical model of the language, statistical language model. There are many other models. For example, another one that we are going to look, actually we have looked at it. Another one is the neural language model that is based on the neural networks. Okay, it's called the NLM, neural language model. That's a very successful model too. And neural language models, actually they started doing better than the statistical language models, maybe for the last 4 years, maybe 5 years. But before that, nobody was able to beat this simple statistical language model. Whatever however complicated model you use, statistical language models were better, okay? But nowadays, neural language models are doing better. There are some hybrid systems that are using the ideas from both the neural models and the statistical models. So you might say, why are we looking at this statistical language models and if the neural models are better? Well, I mean, this is where the most of the ideas come from. This is where the basic natural language processing terminology comes from. And if you read a paper, our graduate students are going to read, they will talk about statistical language modeling. These are the reasons, and also, I mean, the way we are using statistics and probability and the conditional probability is very simple and elegant, and it might be very useful for you to use in other areas. That's why we are looking at this one. Okay. So this is what we are going to do. Okay. If I am trying to measure this probability, its water is so transparent that I observed this word, W1, W2, 3, 4, 5, 6. I observed these 6 words, and I'm asking what is the probability that after these words I'm going to observe the. Okay, so the regular conditional probability says that measure this one. So it's like you might say that this is my event A and this is event B. Remember, patient has fever and I am asking if the flu is causing this symptom. Okay, so in that case, how do I calculate this one? I would say A and B happening together over P A, right? That's what I am doing, right? So this is how many times I have seen water is so transparent that, okay, that's the probability. And how many times I have seen it is water is so transparent that, okay. So if you type these to Google, you will get 0 and 0, right? Google will not say anything about them, but I mean, usually, no, it doesn't give you 0 and 0. It gives you some funny number. Do you know what the number is? This is not 0 and 0, it is greater than 0. You know what those numbers are? Google says that I have seen these words together this many times. You know where those numbers come from? It comes from the book slide. These are the slides from the book, right? Whoever copied these slides from somewhere and made them available on the web, so you get them. You get them. Actually, can I do this? Can I copy it? Yeah. If I copy and paste this to Google, its water is so transparent that I am sure it is going to happen more than 10 times, maybe hundreds of times. Yeah, see, it is 12,000 times. And every time it happens, comes from this EDU side. It's all universities, and these are the slides. Wow, see, do you see that? So everybody is studying this book. It's not a bad book. So it is all you, Alberta. Yeah. And the same slide set. Can you believe that this is happening 12,000 times? Okay, it is only coming from this. Okay, if I remove this so, it will happen probably 0 times or 3 times. Yeah, somebody is doing this experiment. Yeah. Okay, so what I am trying to say here is that if I didn't have these words in this slide set, Google was probably going to say 0 and 0. So this is 0 and 0. I wouldn't calculate anything. If it happened 2 and maybe 2, 3, 4, 5 times, that's not a reliable statistics. Okay. Out of 1 quadrillion, what was the name again? Quadrillion. What does that mean?
1 million by billion, trillion, then quadrillion.
Really?
Quadcopter is a helicopter that has.
Yeah, I know what quad is, but what is quad? Okay, 2 to the power 4, 10 to the power kind of 4 times. Is that? But 1 billion, then what did you say? Billion, then
Trillion,
trillion.
quadrillion. 1 to the 50.
Okay, it is quadruple. Okay, triple. Okay, billion. Okay, so it is like billion times billion, billion times billion times billion. Okay, so out of that many, I am not going to say that word. Out of that many words, if this is happening once or twice, it could be out of luck. Okay, I don't trust that kind of a statistics, even if it happens once or twice. So I cannot use this by the definition of the conditional probability as it is. I have to do some work. So okay, I have to do some work. So it's going to be 0 or 0, and I don't trust that one. So it says that when they originally prepared these slides, when they do this search on Google, it happened 3 and 7 times. So this was maybe 10 years ago. I don't know, maybe 10 years ago. Now it is happening 12,000 times. So are there 12,000 universities in this world? Really? So some universities might be doing it. In Turkey, it is 36,000 times.
No, but it's so transparent.
Oh, it's so transparent. I keep forgetting about it didn't happen. No, in Turkey, no. How about just American universities? It happened.
370 times.
So where did it come from then?
Indian universities.
No. Where does it come from? So it must be some people copying it and putting it somewhere. Okay. It is not coming from the universities. It is coming from some backup sites like the Wayback Machine or something like that, right? Yeah, something like that. So at USA it is turkish.edu 270 units, so that's a better number. In Turkey, nobody put these slides in their size. Okay, go back. So this is not a reliable number. We can't do that. That's why we are going to do something. So for the most sequences, even a sequence like that, I cannot assign a probability to it, and I have to calculate this probability for even longer sentences. So what am I going to do? I have to come up with a solution. We are going to use chain rule of probability. This is this. What is this? What is this? P A B. You know this one, right? This is we have already did that. This is P B A times P B, right? It's just another way of writing the conditional probability, and that's it. Okay, so let's say I am going to do the same thing, but I am going to calculate P A B C. What does it tell me? Okay, so let's think this BC as like a B. So can I do this? P A B C times P B C. Okay, and then maybe for this one I can write the same thing. P A B C times P B C and P C. So this is called the chain rule. Okay, all I'm doing is I am applying the definition of the conditional probability over and over again, and I can make this a lot longer if I like to. So instead of calculating these three words together, right? How many times did I see these three words together? I am trying to calculate it with the one-word probability and one-word probability and two-word probability. So it is easier. It is easier, but it doesn't save me from the bad thing. So instead of calculating 5 grams, I have to calculate 4 grams, which is still expensive. Instead of calculating 10 grams, I have to calculate 9 grams, which is still expensive. So what am I going to do? I have to do something else. But let's look at this chain rule more carefully with the help of the book. Okay, exactly what I said. If you have a sentence like this with n words, express the same probability exactly px1 times given x1, x2, given x1, x2, probability of x3, etc., and go that way. So definitely, I can calculate this one. How many times the word "the" happened in Google Dictionary? Yeah, Google Core. I can do that, or I can do that maybe. But when it comes to this one, of course, this one is easier than this one, but it is still not possible. I have to do something even more to calculate this probability for the whole sentence, and that's where the main thing will come in the lecture. So the chain rule is this. This is completely equivalent to that one. There is no approximations here. So when you calculate probability of its water so transparent, you multiply its probability of its times given its probability of water, given its water probability of was, and it goes that way. So if you do this multiplication, 1, 2, 3, 4, 5, probability calculation and multiplication, you will end up with the probability of this sentence again. Calculation of this one, estimation of this one is not easy. Okay, so for that, for that, I will make an assumption. Okay, here comes the approximation. Here comes the approximation. Okay, it's called independence assumption. Okay, so people say that what is the probability of given? The other day I was walking along and I saw a, then given this sentence, lizard. They say that probability of this one and this one are about the same. They are about the same. Okay. Why? Because, I mean, doesn't matter what you were saying at the beginning of the sentence much. I mean, the other day I was walking along, okay, and I saw a lizard, or I saw a elephant, or I saw a car. Their probabilities are probably the same. It doesn't matter what I had said before. Okay, so again, this is the independence assumption. What I said, I am independent of what I said before. This is not perfectly valid, but it's kind of an assumption, approximation. That's what we are going to say actually. It's like this, okay? I am a doctor, somebody comes to my office. He says that his fever is 38 degrees today, okay? It was 37 yesterday, 36 the previous day, 36 and 36. And given all these, what is the probability that I have flu? Okay, probably my doctor will say that, okay, if a person has this kind of a history, okay, this is today, previous day, the other day, 3 days ago, 4 days ago, okay? So if this patient has this history, maybe I would just ignore these three numbers. Maybe instead of calculating this one, maybe I should just calculate if this person has 38 degrees today and 37 degrees yesterday. So these two are probably equal. I mean, it is better than doing nothing. It's just an assumption. Just an assumption. If it is difficult to calculate this one, then maybe even I am making this even more strong assumption, and I am going to ignore what the patient had yesterday. Just if it is 38 today, then I am going to calculate having a probability of flu just now, right now. Okay, so this kind of independence assumption, again assumption, okay, just to be able to calculate that probability, I will make that assumption. Most of the time, it turns out that this is a very valid assumption, and it holds very nice. It holds very nice. Basically, this is what I am going to say. I'm going to say that to estimate a word's probability, it is enough to look at the previous word and the word before it. Okay, so this is fine. This is fine. When it comes to this one, I will just ignore this one. Okay, and when this comes to this one, I will just ignore this one and this one. Okay, so at most I am going to look at trigrams, 3 grams. Why? Because I don't have to calculate the probability of these 5 words coming together anymore. I am calculating these 3 words coming together, and these 3 words coming together, and this one coming together. So this is exact probability. Exact probability. This is probability of assumption. Okay, some assumption, but these are very measured assumptions, very safe assumptions, maybe. And if I multiply all of them together, I will calculate the probability of almost the probability of this. Its water was so transparent. Okay, so that's what I'm going to do, and this is called independence assumption. Markov formalized it, Markov assumption. Okay, it says that, okay, it says that if you are calculating a probability like this, W from 1 to n minus 1, given all these words, the probability of n, okay, you can ignore how many words? You can use only the last capital N words in your sequence. You don't have to use the whole word. So if I am doing this with the bigram version only, ignore all the words other than the word just before you. It's called the bigram version of the Markov assumption. Okay. So it holds very well. It works very well, and it is better than doing nothing. And as the evidence shows, this language model, statistical language model, works very, very good. Works very, very good. Okay, any questions about this Markov assumption? That will basically make it possible for us to calculate the probability of complete sentences, for probability of the whole document, okay, whole document, by calculating the bigram probabilities. Okay, so it is easy to calculate the bigram probability. For example, again, if I come here, so I'll have what is the probability of its? Okay, this will happen in English this time. Okay, what is the probability of water its? So I'm going to, how am I going to calculate this one? It's going to be probability of how many times I have seen its water over probability of its, right? And times I am going to do this, its water, right? So probability of its water, so over probability of its water. So this is the trigram that I have to calculate. But the next one is, again, it's going to be trigram, and this one is going to be trigram. So I am at most estimating the trigram probabilities, and that should be it. That's it. Okay, that's it. That's called the chain rule with the independence assumption due to Markov assumption. And estimating bigrams or trigrams is very easy. If you use the maximum likelihood estimate, this is how you calculate it. You count all the Wi minus ones, okay? If let's say it's water, okay? So calculate the count of its, how many times it's happened in the Google corpora, and count how many times its water was counted. Okay, so if you divide these two together, you get your probability. Okay, so it is as simple as this, and if you multiply together, you get the whole probability. Let's do an example. Let's say instead of Google corpora or the Brown corpora, my corpora is just this. Okay, I have this simple sentence set. I am Sam. I think this is from Dr. Seuss. Okay, little children's book sentences. Start of sentence, end of sentence. Okay, so there are 1, 2, 3, 4, 5 tokens for the first sentence. Okay, I am Sam. Sam, I am. I do not like green eggs and ham. Okay, so let's calculate all these bigram probabilities. Given start of the sentence, what is the probability of I? Okay, let me. Given the start of the sentence, probability of I is, probability of the S is 1, 2, 3. It happened 3 times, the count of S. Okay, how many times S and I happen together? 1 and 2, so it is 2 over 3. So this probability is 0.67. Okay, And this probability, start of the sentence, given start of the sentence, what is the probability of Sam? It is 1 over 3, okay? Given I, what is the probability of Am? It is this one. So I can calculate any bigram probability that I want. What is the probability of given nuts, okay, eggs? What is this probability? So I need to calculate how many times that happened. One, just one, didn't it? Right? Just one, didn't it, right? Right. D. Okay, just one. So how many times not eggs happened? 0. It looks like this probability is 0. But this is maximum likelihood estimation anyway. I mean, if somebody says that the probability of this happening 0, that's not probably correct, because in this life, everything is possible. Okay, especially with divorce, it can happen. So probability of 0, we don't like something like that, but maximum likelihood estimation says that explain your data the best way. So we will have some solutions for these kind of problems, because if 0 comes to this, if 0 comes to this equation somewhere, since this is a multiplication, we are in trouble, right? So maybe I shouldn't assign any zeros to anything, but this is at the beginning, we are going to put up with it, and later we are going to find solutions for this problem. So I did this calculations for these biograms, and since this is a very simple sentence set, don't expect anything out of anything meaningful out of this one. Okay, so this maximum likelihood estimation is, okay, as I said before, estimate of some parameter of a model M from a training set T. I have a training set T, and I am trying to estimate the parameters of the model. Okay, it is the estimate that maximizes the likelihood of the training set T given model M. So it is trying to explain this data set, maximizing my parameters over this data set. But this data set is not the whole world. Google corporate is not the whole world, or the broad corporate is not the whole world. It changes from time to time, okay? So I will not talk about this much, and we will going to come back to it, okay? So a little bit more complicated corpora, Berkeley restaurant project sentences. I think there are a few thousand sentences in this corpora, and sentences are like this, okay? These are all about the food-related stuff. For example, can you tell me about any good Cantonese restaurants close by? That's one sentence. Mid-price Thai food is what I am looking for. Tell me about this food. I think this is Mexican, Spanish. Okay, can you give me a listing of the kinds of food that are available, etc. So there are a few thousand sentences like this, and we like to be able to calculate probabilities of sentences using this corpora. That's what we are going to do. Okay, so this is good. There are close to 10,000 sentences, and as you see for the bigrams, I want occurred, I want. So these are the counts of I want. How many times I want occurred? It occurred 827 times. For some reason, I occurred 5 times. I don't know why. Maybe a sentence ends with an I, then the other one starts with an I don't know. Okay, we should go back and see. Let's look at these large counts. I want to eat See, these are some very nice grammatically correct pairs, right? So it is capturing the syntax of the language. It says I want, okay? It says want to, okay? Remember with the want, it's a transitive word. It says want to do something. After the want, the word want, we have the word to, okay? To eat again, this kind of stuff. What else? Look at this one. Chinese food, okay? It invented like capturing the meaning of the pairs actually. You say Chinese food, or you would say to spend, again grammar wise stuff. So it is learning eat lunch, again semantic stuff. I don't eat books, I read books, but I eat lunch, right? Grammatically correct and semantically correct too. So it is favoring grammatically correct and semantically correct pairs, okay, by doing the simple counts, and I don't have to teach these one by one. For example, in the if I calculate the count of he goes and count of he go, okay. Of course, you would expect that the count of he goes is much higher than the count of he go. So that means what? We learned about the morphology of and the syntactic rules of the language too. So I prefer this morphological form of the word go. Okay. So again, this is very effective. What else? So these are the unigram, single gram, 1 gram counts. I happen this one, won't happen this much. And these are the probabilities actually. These are not the counts. How do I calculate the probabilities? You divide them by the total number of words actually. So if you put them together, this is what I get. See, some of them is happening a lot. I want is like, okay, this is the probability of, okay, this is not the probability of I want. It's the probability of given I, what is the probability of want, right? So because this is too big. By the way, the total of this line should add up to 1.0, right? Is that correct? Even I, what is the probability of all the words? Okay, it should add up to 1.0. Does it? 33, 36, it is like maybe total is 70. No, it is not bad, no. 33 is here, then this is very low, this is very low, this is way lower than 1.0. So what's happening? Why it doesn't add up to 1.0?
It doesn't have to.
What?
It doesn't have to add up to 1.
It has to add up to 1. I mean, given the word I, what is the probability of the next sentence? If I replace this X with all possible words, they should add up to 1. What is this meaning? Okay, given the word I, what is the probability of what? It says it is 30%. So 30% is very high. It is not the probability of I want. It is the probability of given I, what is the probability of want? Okay, so if I replace this want with all possible words and take their probabilities, it should add up to 1. But I am adding them up, and no, it is not happening. It is not 1.0. Why it's not happening? Anybody from the online audience? Why didn't I get 1.0? The same thing is valid for the columns too. This one should add up to 1.0, but it's not happening. The answer is very simple, it's not complicated. This is what I know. I mean, if I replace this x with all possible words, it should add up to, okay, for all the words in my dictionary, this should add up to 1.0. And it's not happening here. Why? Why?
Calculate the probability or counting of the verbs.
No. The problem comes from here. 1, 2, 3, 4, 5, 6, 7, 8. I have only 8 words here. Do I have 8 words in my dictionary? Of course not. Out of 9,000 sentences, there should be at least 10,000 unique words, right? But this table is not complete. If I give you the whole table, it would be a 10,000 by 10,000 matrix, right? And most of it would be 0. But if you add all the numbers together, okay, for each line and column, you will get 1.0. Okay. So let me take 10 minutes of break. After the break, we will continue. So let's be here around 15:35.
böyle sınıf çok geçmişse eğer zaten onu bilemem. Çalıştı gibi yani. Teksti mi yazıyorsunuz?
Kitabın tekstine baktım, dedim olarak belki birazcık benzeyen şey yapabilir. Aklımda sadece kelime. Bilmiyorum, benzeyen kimse de
Senin dediğin şey var mı? PDF text. Şeydeki, Windows'daki konuşmanı ben dedim. Ondan aldım. Daha sonrasında şey var.
o şey, onu Linux'ın bir büyüklüğü. Onun böyle format merkez Ben sana PDF text için dönüştürmek için.
pdf-text.com
.com online mı dönüştürdün?
Zaten ilk başta baktım da çok uzun sürüyor. Bir de düzgün çevirmiyor. Türkçe karakter falan atlıyor. Veya bazı karakter atlıyor. Sen düzgün çıkartın. Nasıl bir tane kurulum dedim ondan şey yapmış.
Yani biri Linux'taki PDF text.
Okay, so bigram probabilities are here and our unigram counts are there, and we can calculate maybe some stuff. For example, when I say what does this say? This says that the probability of sentence beginning with an I is 25. So it's very high. So at the beginning of I would say I would, it is 6%, okay, and 4%, 2%, etc. So these are I want, I would, I don't, I have. These are very high probability bigrams, okay. So sentences start with either a pronoun or a verb, okay. After I would use want, would, don't, have, etc. After to, I have a verb coming together. After British, I will say food, restaurant, cuisine, etc. So it is capturing lots of data from the language itself, syntactically, semantically. Also, it is capturing data from the world. Okay, this is about geography and etc. Okay. So, other stuff, for example, this one is talking about eat, after eat what comes. These all make sense. I mean, higher the probability, better the chance of using it. And if we like to put together all of them, I want to eat British food, okay? So what is the probability of I want to eat British food? So usually what we have is use the regular, the standard definition of the conditional probability, but that requires calculation of the 5 grams, which is to by the way, Google couldn't calculate 6 grams because that many words, that quadrillion quadrillion kind of words, it was not enough to calculate 6 grams, okay? You need more data to calculate 6 grams, so they calculated at most 5 grams, okay? This one is asking for 6 grams, which is not possible even with the Google. So I have to use that Markov assumption. What do? I calculate given S probability of I times given I probability of 1, etc. If I multiply them together, this is the final result. Okay. But this formula is kind of wrong, right? It is missing. It is missing something. Tell me what it is missing. This is not exactly the chain rule or the approximation of the chain rule. It is missing one component. Do you see what?
Probability of ilk şeyin probabilitesini vermemiş öyle.
Probability of, exactly, probability of S, right? Probability of S. So what is the probability of S? Let's find it out. Well, unfortunately, they didn't give me. So probability S is the number of sentences over the number of words, right? How many sentences I have? 9,000 sentences. How many words I have? I don't know, maybe 100,000 sentences. So the probability of S is going to be maybe probability of S is going to be maybe 0.08 or something like that. So if I multiply it with this one, I would get the probability. So do you think this probability is too low? It is 0.00016. I want to eat British food. It's a perfectly legal and nice sounding sentence, right? Why is it so low? Why this probability is so low? I mean, when you see that, you would expect that, okay, maybe this is not a meaningful sentence. That's why the probability is low. No, the probability is low because it's not a bad sentence, it's a good sentence.
You don't have a causal preference to compare to other valid sentences similar to it.
Yeah.
You
Well, I mean, yeah,
normalize it.
these probabilities are not meant to be evaluated as an absolute value. We are trying to compare sentences with sentences, okay? And the other thing is that this is just one nice valid sentence, grammatically and semantically valid sentence, right? How many grammatically and semantically valid sentences are there in English? Infinitely many, right? So if I add the probabilities of each of them, they should add up to 1.0, right? So that's why each grammatically valid sentence might have these kind of low probabilities. Okay. So suppose I don't have this. I am doing spell checking. Somebody write this. I want to eat British folks. Okay. There is no such word as folks. Okay. So I calculated the edit distance between this misspelled word with lots of words, all the words in English. So it looks like I have food, I have fool, I have food. These are all same distance words to fools, right? I mean, they are just one replacement. So edit distance is not giving me any one answer that says that this is the shortest distance. It will give me three words. So what would I do? I would put each of them to this probability calculation, and I would choose the one that makes more sense, that produces higher probability values. So I want to eat British food, doesn't make much sense. I want to eat British food, no, doesn't make much sense. I want to eat British food, well, I'm not choosing them because it makes sense or not. Most probably this British food is going to produce the highest probability, and I will pick them. So this is a one nice spelling correction example that you can have. So feed this. Calculating edit distance is something nice, but it is not the whole story. You have to be able to select the correct word by looking at the language model. So I have the nice edit distance measure that eliminated lots of words, but now I have this nice language model that tells me which sentence is better than the others using these probabilities. Okay, good. Suppose I'm doing the same thing with Turkish. Okay. In Turkish, it's going to be a problem. Let's try to translate into Turkish. İngiliz yemeği yemek istiyorum. İngiliz yemeği yemek istiyorum. Yemek, yemeği, yemekten, yemekler, yemekte, yemeğe. These are all related to the same word yemek, right? Okay. So should I count them as different words or should I count them as the same words. If I count them as different words, okay, there are more than 2,000 different forms of the same verb in Turkish, they say, right? So that's going to make my statistics a lot complicated. My table sizes will be a lot larger. But if I don't count them as different words, then grammatically my sentences will not be true. So even for Turkish, even this kind of a simple word counting is difficult. And for English, it was easy because, I mean, what could happen? It is either eat or eats, okay? It would be I is I always. Want is want or wants, that's it. To is to eat or eats. British, food or foods. Oh, is there foods? Is there such a word as foods? There is no word as foods, right? No, it's not countable. Okay. So, I mean, so possibilities are not that much, but in Turkish, when you say İngiliz yemeği yemek istiyorum, okay. Yemeği, it comes from the same yemek word. Yemeğe, yemekten, yemekte, yemekler, yemekleri, yemeklerimiz, yemeklerleri, etc. There is no yemeklerleri. But you know the idea, right? So counting the Turkish words is difficult. Okay, doing this kind of a calculation is difficult for the Turkish language. Some people do this. Some people say that I'm going to take the root of it, root of the word, okay, and count the root and ignore the inflections of the word. But again, that's a problematic. What is yemeği? What is the root of yemeği? Is it yem or yemek, right? So there are many different variations. Morphologically, there are many ambiguous parts of each word, so it is difficult. Some people do this. They say that I will take only the 5 letters, the first 5 letters of the word, and I will count them. Only the 5 letters. Okay? So I will ignore the morphology. I will ignore anything else. So this is going to be just an approximation. So I will do that. That would make kind of sense. I don't know what the best solution is, but your second homework will be about this. This is what's going to do. Again, we are going to use the syllables again. We are going to separate the words into syllable, and we are going to do the engrams of the syllables, not the engrams of the words. Okay? In Turkish, we are going to do the engrams of the syllables. For example, when you say İngiliz yemeği, it's going to be yemeği. Okay, it's a trigram. Okay. So the nice thing is that how many syllables are there in Turkish? We have to calculate this, right? It was 30 to the power 3 or something like that. So it is not much, right? Something like that. And most of them will be empty because you cannot have a syllable like KKK. Okay. So it has to be, no, it is much, okay. It has to be, if a word starts with a vowel, it has to end with a consonant, right? So 8 times 20 is here, and 20 times 8. If a word starts with a consonant, it has to be a vowel and a consonant. So it is 28 and 20. What else? And I have sometimes consonant, vowel, consonant, like Turk, right? So 28, 20, 20. It's not much. No, it's not much. So our tables could be, our tables that keeps the engram information cannot be that large. Of course, again, many things are not possible, but our tables will be sparse, but you can use some tricks for keeping the sparse matrices like those. Okay. Good. Maybe we can do a spelling correction application for that, yeah. Could be. Okay, so bigram estimates of the sentence probabilities are calculated that way. So I am estimating the I am estimating the probability of a sentence. And again, here, this is what I said, right? When you say want English, want Chinese, okay, word knowledge, Chinese food, etc. To eat, want to food, okay, syntax, and discourse, okay. Discourse is, remember, what kind of sentence should I use under what kind of circumstances, okay. Each sentence starts with an I. Somebody's talking, I am talking, okay. So this guy, Shannon, you know this guy, right? Shannon is a very famous computer scientist. 1950s, he invented the information theory, and they say that the information theory is as important as the quantum theory or the particle physics, because while he is what's happening, I had enough space, didn't I empty my okay, so I had 12 gigs of this space. What's okay? I'm going to. Where is my? Do you guys see my recycle bin? No, you don't. Here is my recycle bin. Do I have enough space now? Not. So what should I do? Didn't I erase this video? Yeah, I have erased it. I don't know where else to look. Oh, I know. Okay. You close your eyes. I need to erase some videos from my Amazon stuff. My downloads, okay. What? Oh, is it because I don't know, okay. I will, okay. That's the recording for the local recording only. So Teams is recording. So we will use Teams. But what happened to my robot? Something is funny. Okay, so this guy invented the information theory, and he said that if we have a language model, that statistical language model, then that would be very useful to measure how good the sentence is. It can be also used to generate artificial sentences. Okay, it can be used for generation. For example, I know that a sentence that starts with this sign, right? Given the beginning of the sentence, what is the probability that makes what is argmax x? What does that say? Somebody read this formula for me.
The X that maximizes the probability.
Say it again.
The X that maximizes the probability.
Okay, return me the x that maximizes this probability. So for our restaurant case, it's going to be probably I, right? So this produces I. And then I will ask this question. Okay, I will ask this question. What is this X? Okay, given I, what is the probability of highest probability word? Probably it's going to be 1, right? And if I continue that way, probably I will get this sentence, I want to eat, for example, food, and end of sentence. Right? So I produced a very likely sentence out of my model. If I run this algorithm again, it will produce exactly the same thing, right? I don't want to do that. I don't want to produce exactly the same thing. This is what I'm going to do. This is what I'm going to do. Instead of choosing the argmax, okay, instead of choosing the maximum of it, okay, I will say that I will choose a high probability word. Okay, I will choose a high probability word, but it's not the high, it's not the highest probability word. That's the algorithm. Okay, let's say the probability of the is very high. It is 0.06%. Okay, probability of is high again, 0.3%. And probability of A is high, 0.2%. 2 is, so if I put all the probabilities together, this is what I'm going to get. So all the words are here from here to there. So the total probability is 1.0, okay? So all I need to do is pick a number, a real number between 0 and 1. Let's say I hit 0.31. So go on this line, find the 0.31 place. Which word does it belong to? I will pick that one. So in this procedure, D has the highest probability because it occupies the largest space. Of is next, A is next, 2 is next. This polyphonic has the least probability of being selected because it occupies very little space between 0 and 1, right? So what I'm doing is with the Shannon's method, okay, get all the words that can fit in here, all the words in the dictionary, okay, put them in a line like this between 0 and 1. This is the word the, this is the word of, I, this is the word very, very small, let's say, eat, and these are the very, very small words, and each of them are like almost no probability. Okay, and then after doing this, just pick a number between 0 and 1. Let's say I hit here. So D has the highest probability of uniform distribution. Okay, this is just a random number uniformly between 0 and 1. D has the highest probability of being selected, but the other ones have the probability of being selected, but they are not as high as D. So that way, I can produce completely random sentences. The nice thing is about this is that, okay, the sentences you are producing will read like real sentences. Okay, will read like real sentences. Okay, something like this. This one, it picked the I first. Then I asked the same question. What is the highest probability after I want? Then two. So it is. I want to eat Chinese food. Okay, so people did this experiment instead of training this on the restaurant data set. They trained on all the works of Shakespeare. Okay, this English poet Shakespeare, and my model is Unigram model. So my model is, remember the chain rule. Okay, my assumption was with the Markov assumption. It was word and from word 1 to word n minus 1. Okay, Unigram model says very simple. Ignore all that you have seen. So this is almost the same as PWN. No prior probability, just a probability of the word itself. Okay, this is Unigram model. This one is, again, assumption, bigram model. Wn is only dependent on n minus 1. More complicated. Bigram, of course, you expect that bigram is doing better than the unigram. And the third one, maybe Wn depends on Wn minus 1 and Wn minus 2. Or wait, just let me fix the order. Order is not correct. 2 and 1. Okay. So unigram, bigram, trigram models, and this one produced Shakespeare using the unigram model only. It just puts words one after the other because it doesn't pay attention to the previous words. High probability words. Doesn't read very well. To him swallowed, confess here both, dot, which dot, of save, no meaning whatsoever. But when it comes to trigram or quadrigram, okay, fourgram words, okay, look at this one. King Heribert, I will go seek the traitor Gloucester. Exalt some of the watch, a great bank, sir, then, will you not tell me who I am? This is not from Shakespeare, this is our quadrigram model, okay? Indeed, the short and the long, marry this noble Lepidus. I mean, I never understood what Shakespeare is saying when I read it. I don't understand this one either, but to me, this looks like Shakespeare, okay? To me, this definitely doesn't make any sense. There is no grammar in it. Every enter now, several so that, no, but it cannot be but so. So let's look at this one. Shakespeare, for certain, said it cannot be but, because this is a foreground based stuff. Shakespeare also said somewhere, cannot be but so, but Shakespeare may not have said it cannot be but so. So if you combine these together, it looks like Shakespeare is telling you something, okay? But Shakespeare never said anything like that. So this is produced using the Shakespeare data set. If you train it on it, and if you ask the Shannon's algorithm to produce a sentence, it produces it. Unigram doesn't make much sense. Quadrigram is quite good. Trigram is not bad either. Okay. Indeed, the Duke and had a very good friend. Okay. This shall forbid it should be branded if renown made it empty. Well, doesn't make much sense to me, but again, Shakespeare doesn't make much sense to me either. By the way, these are the stuff for Shakespeare, okay? Shakespeare used almost 900,000 tokens in his works, and he has a vocabulary of size almost 30,000 words, okay? And it produced 300,000 bigrams. Where does this come from, 300,000? It is the square of this number, right? Or is that? No, it's not. What I'm saying is not correct. Okay. Square of this one is what? This is 30,000. Okay. Square of this one is, what is my size of the, how many possible bigrams are there? It is 30,000 by 30,000, which makes it 9, 1, 2, 3, 4, 1, 2, 3, 4. Okay. 900 million possible bigrams. Okay, is that correct? So 900 million possible bigrams, but Shakespeare only produced 300,000 bigrams because most of those bigrams doesn't happen at all. right? It doesn't happen at all. So that bigram matrix is very empty. It is 99.96% of it is empty. That's a big problem with the language modeling. Okay, this is just bigrams. For the quadrigrams, it is worse. It is 99.9995 is empty. Okay, so it's a these are very sparse matrices, and we have to find a way of dealing with it. So you shouldn't maybe use 4-dimensional vectors to represent these. Maybe you should use maps, right, from Java or C++. Well, I mean, it's your problem. You are going to do it yourself. By the way, if I train my model not on the Shakespeare but on the Wall Street Journal, you know, Wall Street Journal is a journal in the USA-based journal, USA-based newspaper. It mostly talks about the financial world, but it has lots of news about the international events too. So Unigram doesn't make much sense, but if you look at this one, Trigram, they also point to $99.6 billion from 246.3% of rates of interest stores as Mexico and Brazil on market conditions. So if you read it, okay, for a while you think that it makes sense. I mean, grammatically there is nothing wrong with it. It has all the sub-phrases available. And in fact, it talks about Mexico and Brazil. It doesn't say Mexico and Iraq, right? So those kind of stuff. And it says market conditions. It gives me nice $1 billion kind of stuff. It doesn't say quadrillion dollars. $1 billion makes sense in today's world. It looks like it is producing something meaningful. Of course, there is no meaning in it. It is just a statistically high probability sentence. Okay. So I didn't teach anything about the grammar of the language. I didn't teach anything about the morphology of the language. It doesn't say market condition, it says market conditions, right? Grammatically correct. Okay, so how do we evaluate our models that we have formed? I mean, it looks like trigram models or quadrigram models, 4-tuple models, 4-gram models are better than the unigram models. But how do we know how we are doing in terms of model quality? Which model is better than the other models? Okay. For this, we have to come up with a measure of it. Okay, evaluation. Okay. With the evaluation, we are going to use the Shannon's information theory again. We are not going to go deep into the evaluation stuff, but this is what's going to do. We will take the whole, let's say, Wall Street Journal corpora, using the 90% of the whole set. I will do all those counting of the words and etc. I will make up my tables and etc. Then I will use that remaining 10% to test my data. How do I test it? I will measure their probabilities. But I showed you some probabilities. What did you get? The probabilities were 0.00016%. What does that mean? Looking at the probability doesn't make much sense. Instead, we are going to look at this measure perplexity. Okay, perplexity. And perplexity is this formula. Okay, is the probability of the test set normalized by the number of words. So it is measuring the number of words. Okay, to calculate the perplexity of this probability if you are using the bigrams. This is what you are going to do. So what does that say? It says that I am going to calculate this probability of 1 over this probability. So probability higher is better, right? So if this is higher, these numbers are going to be close to 1. Okay. If they are lower, these numbers will be very, very large numbers. So I want to have a smaller perplexity for my test case. So what is the perplexity again? You are calculating your probabilities. You divide them by 1 so that the highest probability, which is 1, will produce the smallest number, but no sentence will produce you a probability of 1. It will be between 0 and 1, but I like those numbers to be close to 1. And multiply them together and take the square root of n. So the square root of n, root of n. So this will normalize this probability by the number of words. Because if you have 15 words in a sentence, this probability will be small. I don't want to be affected by the number of words in my that I have in my sentence. Okay. So perplexity it is not invented by the NLP people. It is invented by information theory people. How much information I have in my message? That's the question. If I am sending one message from one source to the destination, how much information do I have in that message so that I can compress it and etc. We get that idea from them. Okay. So if I compare the Wall Street Journal model using the unigrams and bigrams and trigrams, okay, trigram perplexity is 109. Unigram is almost 1000. So trigram is a much better model than the unigram model because its perplexity is close to 1. You won't have any models that will produce a perplexity of 1, which is the perfect perplexity, because perplexity of 1 means that your word order fixed. You can have one sentence only and nothing else. Okay. Perplexity of 2 is you have only 2 ways to go. Okay, for each word. Perplexity of 100 is you have 100 ways to go for each word maybe. So nowadays, I think our best models are doing 30-40 perplexity of 30-40. So they are good enough to suggest you 30 words for each position, which are valid words for that position. Okay, so lower perplexity means a better model. Okay, I think I skip this part. Let's talk about this part and let's end our lecture for today. Okay. The thing with this approach is unknown words. Okay. Because in my data set, in my training set, some of the words will not happen at all. Okay. In my test case, you will see some new words. So how do I deal with this word? Okay. This problem. So for this, so if one says that create an unknown word token, unknown. So if you see a word, count it as unknown if you don't know that word. Okay. You create a fixed lexicon L of size V. What is lexicon? Our vocabulary. Okay. When you are doing this counting, the unknown words will be counted as just one word. We call them like remember the start of the sentence is this. All the unknown words will be this. Okay. So when you see an unknown word in your test case, you increment the count of this word, this new word. Okay. So it's kind of a backup strategy not to fail in case you see unknown words in your testing. Okay, so this is how you deal with the unknown words. Open vocabulary task means that your vocabulary is not fixed. Every day you may see new words, and when you see the new words, you shouldn't fail. Okay, so you create a fixed lexicon L of size V from a dictionary or subset of the terms from the training set. At text normalization phase, any training word not in L changed to unknown. Okay, now we count that like a normal word. And at this time, we use that unknown count for any word not in training. Good? So that kind of will handle it. But still, we didn't solve the problem of some counts becoming zero. It says food Chinese didn't happen before. That doesn't mean that it will not happen ever, right? It might happen. But if this is zero, then the probability calculations will give me zero at the end because there's some multiplication. That's a bad problem. Okay, that's a bad problem. For that one, we have solutions, and those solutions will be discussed under the title of smoothing. Okay. The fact that you didn't see something doesn't mean that you won't see it. It has a smaller probability, but there is a possibility that you will see it. And maximum likelihood estimation is not a good way of making that probability estimate. Okay, we will do better than maximum likelihood estimation. It is simple, but it is not enough. Okay, any questions? Any questions? Okay, that's it then. Tomorrow on Monday we will have our midterm exam. Okay, see you on Monday.
Do you have any suggestion while we are preparing for midterm?
Do I have any suggestion for the preparation of the midterm? Watch all the videos. Okay, read the book. The chapters are available. I discussed a few things other than the book chapter, like the edit distance, and I discussed about the word to vec concepts, but I provided the slides to you about those, and that should be enough. And ask the other people who took this course previously. Most of them are graduated, but you may find them. Okay. So there would be a few knowledge questions, what is this and this and this. And there would be a few problem questions, calculate this and this and this. What is the result of this, etc. Okay, good. I'll see you next week. And let me not forget about putting the slides into the Teams page. I'm doing it right now.